Why it's not available? So let us go through this example. So first we need to use adaptive linear neuron, which is called AdaLine, which has been trained using a gradient descent. So first we need to use it for classifying iris dataset, and because perceptron can be used only for classifying binary classification problems, so we will read our data. We will select two classes. We will extract the first 100 class labels, 50 for iris setosa, and the second 50 for iris versicolor. And because I want to visualize it in two-dimensional space, I will select two inputs as target feature, as input features. So I will select feature number 0 and feature number 3. So I will run that part, and I will select the first 100 points. Column number 4, it's the targets. So it will be like, those targets will be like this one. So we will have class 1 and class -1, as you can see here. So Y will be column number 4, the first 100 points, and I will replace iris setosa with 1, and the rest will be replaced by -1, which is iris versicolor. So fourth column, or the target feature, it will look like this one. I need to implement my adaptive linear unit. So first, I will use it for prediction. And if you want to use it for prediction, so for prediction, we need to just multiply, we need to calculate net, which will be omega multiplied by x plus b. So this equation, it's dot product of inputs and the weights plus p. So this one, in fact, this equation, it's omega x plus p. After that, we need to use a gradient descent for adjusting the weights. So we will define another function called the training, for example. X will be training inputs, T will be target inputs or labels. This is the cost or the error. We need to just keep it for plotting, for example. We need to initialize our weights by small random values. So we will do it using this command. So omega equal random values of the size of the training inputs plus 1. We will start a for loop, and in each epoch, we will calculate net. So net will be x multiplied by omega plus p. Because we use linear activation function, we need to calculate y. So y will be net, right? Because we use a linear activation function. We need to calculate the error. So the error will be t minus y. We will update the weights. So omega equal omega. Omega plus equal, it means omega equal omega plus eta multiplied by error multiplied by the gradient. I mean, this is a gradient. It's eta multiplied by the gradient. So the gradient will be the error multiplied by the input. We don't need to have this mean value here, in fact, right? Because we are not using batch gradient or mini batch gradient. It's just a stochastic. So we will do those adjustments example by example. So we need to multiply this one. In fact, it's eta multiplied by error multiplied by the input x. And for the bias, it will be eta multiplied by error multiplied by 1. The cost or the error function, cost function, it will be 0.5 multiplied by error squared error. It's called the mean squared error, correct? Mean squared error. So we will take the mean value from each epoch, because we need to plot the mean error in each iteration, for example. After that, we will define our model. So model equal our model. We need to define number of epochs, number of iterations. This is the learning rate. And after that, we will train our model using X and Y, and we will calculate predictions for X. And after that, we will plot our results. So as you can see here, this is a training error over iterations. I trained the model for 10 epochs or 10 iterations. So this one will be the mean error for each iteration. And we need to run that part first. And after that, we need to train our model, define our model, and train our model. We got this kind of, and we will run that part. So as you can see here, okay, we have a problem here. Okay, Setosa versicolor. Our model is not working well. In fact, as you can see, it misclassifies the two classes, right? We misclassify the two classes. So what happened here? X1 and X2, we try to plot our model. I think we have a problem here because we are plotting predictions equal -1. All predictions are -1, right? So the error equal 100%. It should be 50% in fact. Maybe we need to increase this value. Maybe it was not enough. Now all are in the other side. Now it works fine, right? Yes, now our model is working. So now we can get the blue cluster, which is a versicolor in one side, and Setosa cluster on the other side. So now the accuracy is 100%. It's just, I mean, this one, maybe it's not very important. It's just to try to visualize distribution of feature inputs, which might be like this one. And here we try to predict test training and with scaled features. So we try to scale features, normalize, and it trains the model for more epochs. So it will be like this. Yes. So this is one example, which is adaptive linear unit. Adaptive linear unit, it is used usually for regression, but as you can see here in this example, we used it for classification. How can we do this? You just need to calculate net or calculate y equal net, which means we use the linear activation function. And if you want to use it for classification problem, we need to compare this one with a threshold value, right? We need to compare this net value with a threshold value. So for example, if it is positive, if it is greater than or equal 0, the output will be 1, otherwise the output will be -1. So this is the threshold function, which will be used to convert regression problem into classification problem. Yes. So do you have any question, please? Any questions? So we can go back to our slides. So what has been done here? In fact, we just loaded our data. We did that. Loading your data, we used as the first 100 points. Why we used as the first 100 points? Because perceptron can be used only for classifying binary classification problem. Any perceptron is used for binary classification problem. So in this case, we need to limit ourselves to 2 classes. And since this iris dataset, it consists of 3 classes, it will be like this one. The first block, it's 50 points for one class. The second, 50 points, and the third, 50 points. The first is iris Setosa. This one, it's Setosa. The second, it's a versicolor or versicolor. And the third one, it's a virginica. So it's 3 types of species. And the input, in fact, we have 4 inputs. So the 4 inputs are petal length, petal width, and sepal length, sepal width. So the data set looks like this one. We have X1, X2, X3, X4, and this is the target features T. So we just selected, I mean, because we need to visualize it in 2-dimensional space, I selected column 0 and column number 2. So we will select this one and this one as inputs. And we use the first 50 and the second 50. So we used only 100, right? So we selected here from 0 to 100, the first 2 and first column and the third column. And for the target, we selected the first 100 points. And after that, because the target, it's labels. So it's iris setosa, iris versicolor, for example. We need to replace it with a numerical value. So I replaced the first label by 1, and after that replaced the second by -1. This is our model. We need to define this adaptive linear unit, for example. So we need to initialize it. We need to select number of epochs. We need to select learning rate, for example. Those are the default values. We need to define a function for prediction, right? So this function, in fact, it's net equal omega x plus b. And after that, we will compare net with 0. So if net or y of net equal +1 or -1 +1 when it's net greater than or equal 0, otherwise. So it will be like this one. This function here, we used it for training our model. So first we need to initialize the weights. Those weights we need to initialize it with small random values. And after that, you need to calculate net. Net equal the same, this equation, omega x plus p. We calculated net. And from net, we need to get y. We have linear activation function, so y equal net. The activation function is like this one, right? So when the input is net, y also is net, because this is a line with an angle of 45 degrees. So if net equals 0, y equals 0. If net equal 1, y equal 1. If net equal 100, y equal 100. So y equal net. So we have this one, y equal net. And after that, we need to calculate the error value. Why is this error? Because delta omega equal eta multiplied by t minus y multiplied by x. So we need to calculate that part, t minus y. So delta omega will be eta multiplied by the dot product between t minus y and x. It would be like this one. For the bias, it would be the same. Delta b, it will be eta multiplied by just t minus y. So it will be like this one. Correct? And after that, we need to calculate the cost. The cost will be error equal 1 divided by 2 t minus y squared. You can put it here, I, for example, I equal 1 to 100, right? So we just need to calculate this value. So we can calculate it for each epoch and we can plot it. It's a summation, in fact. So it's error square. So it's summation of this one, summation of error square. So it's the same equation here. We will train the model for 10 epoch using this learning rate, for example. So we will train the model using x and y. And after that, we will use x for making a prediction. We will compare those predictions with the target to calculate the prediction error, for example. And as you can see here in this graph, when we are starting at iteration number 1, for example, we initialize the weights. So we should expect that we initialize the weights with random values. So we should expect that the performance will be very random at the beginning. So at the beginning here, the classification will be very random. So the error is very high. And in iteration number 2, we adjusted the weights a little bit. So this error goes down. And in the third iteration, it goes further down. And so on until we reach a very low value, which is close to 0, right? So when it is close to 0, it means your classification accuracy will be 100%. So you need to select enough number of iterations in order to be able to get better performance. If you stop the early here, for example, maybe the accuracy will be 80% or 85%, which means you need to train your model for more time. Use a scatter plot for plotting two classes. We have one class above the line and one class below the line. And this is my line, right? How can we plot this line? Using this equation. I mean, just to remember, it's omega x, omega 1, x1 plus omega 2, x2 plus p equals 0. This is my decision line, in fact, right? If you know omega 1 and if you know omega 2, just assume values for this one. It's x1. And this one, it's x2, correct? And we will plot the line. So just assume values for x1 using this one. Assume some values for x1, substitute those values into this equation to get x2. So x2 will be minus 1 divided by omega 2 multiplied by omega 1 x1 plus p. If you know x1, you can get x2 and plot the line. It's just how to improve gradient descent by feature scaling. Sometimes it's important to try to do some scaling or standardization, for example. I mean, scaling, it means we will divide each input feature by the range, right? Because we need to put it in the range from 0 to 1, for example. So we need to do it. We need to do like x equal x minus x minimum divided by x max minus x minimum. It will be like this one. This is the range. And so subtract each value from the minimum value and divide it by the range. So in this case, all x values will be between 0 and 1. Standardization, we try to standardize so we can shift the mean and variance of each feature so that it is centered at 0 and has a feature standard deviation of 1. So it will be x minus mu divided by sigma. Mu, it's the mean, and sigma, it's the standard deviation. It should improve your performance. You have another version here if you want to go to this version 2. Okay, so it's the same, I guess. Yes, this, if you want to go to this code. We have here an example. Maybe we need to finish with this example, this first session. If you want to use adaptive linear unit for predicting, for example, your annual salary. So you can go to this example here. We have a regression salary dataset. And in this example, you have, we try to predict your salary as a function of years of experience. So for example, if you have 0 years of experience, you will get this amount of money. If you have 2 years of experience, you should get this amount of money. If you have 8 years of experience, you should get this amount of money, right? So now we will build a model to make this kind of regression. And after that, you will use this model for predicting. So for example, if you try to hire someone and this person has 6 years of experience, so in this case, you will just draw a line. It will intersect this green line in a point and just extend this line in the other side. So he should get this amount of money, for example, per month, right? So we can use this one for regression. And I just here we have only one input, correct? So the model will be like this one. So we have omega multiplied by x plus b. So it will be like this one. And you will not do anything, in fact, because you can just get y equal net directly. So even you don't need to plot this linear activation function because y equal net. And those are the coefficients of your model. Please go to this line in the break and try to look into it. And if you have any questions, we can talk about it. So this is the learning rate. I mean, the problem here, sometimes the learning rate has a huge impact on your system stability and robustness, for example. So you can just train the model with 2 different values, for example. If you will train your model with very, very small learning rate, it will take too much time to converge. So it will be like 5,000 iterations. But if you increase it a little bit, it will converge faster in 50 iterations. So learning rate is very important. So we will stop here, and after that we will talk about the activation function next part. So please, if you have any questions, just try to ask your questions. If you have any comments. I need to check. So we will finish now, and we will start again.